Welcome everybody to today's edition of our webinar on emerging topics in biomolecular magnetic resonance. So both speakers have agreed to recording, so we will do so and then upload the recorded lectures to the ICMRBS YouTube channel. So today we have two fantastic speakers, Rienstra from University of Medicine and Malene Ringkjøbing Jensen. I hope I pronounced it correctly.
More or less.
More or less, okay, good, thank you. So without further ado, then I give the word to Bob Griffin, which will introduce Rienstra.
Okay, well, it's a real pleasure to introduce Chad to you today. He really is a person who needs no introduction. Chad was an undergraduate at Macalester College in St. Paul, Minnesota, and he came to MIT to graduate school, where he graduated from our group in 1999, and that was followed by a postdoctoral position at Columbia University with Ann McDermott for a couple of years. And then in 2002, he joined the faculty of the chemistry department faculty at the University of Illinois. And he stayed there until, that's roughly 2020 or so, something like that, about 18 or 20 years or so. And then most recently, he moved from the University of Illinois to the University of Wisconsin in Madison, where they have a very, very large, well-known collection of high-field NMR spectrometers. Now, Chad has done many interesting things scientifically during his career. When he joined our group, we were sort of in the heyday of developing dipole recoupling experiments, as well as decoupling experiments. So one of the first things he did was a collaborative effort with Andrew Bennett, in which they developed the TPPM sequence, which is very, very widely used now for decoupling and magic angle experiments. Subsequently, he was involved in the development of the so-called RFDR experiments, radio frequency driven recoupling, which is again a widely used carbon-carbon recoupling experiment. And then he also developed a version of C7, which he called CMR7, Chad Michael Rienstra 7, I believe is what it was supposed to be, all right? And then together with Martin Howie, he worked on SPC5 and SPC5-3. Now, he not only developed new pulse sequences, but he did one of the very first structures of a molecule using magic angle spinning, and that was informal MLFOH, a molecule that Mei Hong introduced to our group right before she left. And the interesting thing about this is that there was a very large collection of backbone torsion angle measurements, as well as carbon nitrogen distances. And it led to a backbone RMSD of 0.02 angstroms, which is something that was really unheard of before that. It had a heavy atom RMSD of 0.38 angstroms. So this was really a sort of record for a low value of an RMSD. Now, more recently, when he was at Illinois, he developed the Mississippi sequence, which is used for water suppression, and he did some very nice early experiments on proton detection at, say, 40 kilohertz. And I think what got him tenure was the structure and all the experiments, a big collection of experiments on GB1. And then most recently, he's published a really phenomenal structure of alpha-synuclein fibrils. Now today, he's going to tell us about carbon detection sensitivity and high magnetic fields for solid-state protein structure determination. Okay, so Chad, the virtual floor is yours.
All right, well, thank you, Bob. I'm sharing this way, so I believe that you can see my screen. Is that correct?
That's correct, that's fine.
Wonderful, all right. Thank you, Bob, for the very kind introduction. It was so surprisingly kind, I'll have to skip over a couple slides. Thank you, Art, for subbing for me. When I was originally scheduled to give this seminar, I had COVID back in January, and so I, along with many of you, have suffered from that, both myself and with my family. So we're glad to be mostly out of it, and I hope we do have the chance to meet together in person in August in Boston for the in-person ICMRBS, so I look forward to that. So as Bob mentioned, I moved to Madison here after 17 great years at Illinois at the beginning of 2020. And so I want to talk a little bit about how that move transpired and then some directly related developments that we worked on as part of the move to improve carbon sensitivity, especially at ultra high or high magnetic field. Okay, so as many of you know, John Markley established NMR FAM over 30 years ago. And more recently, Katie Hensler-Wildman moved from WashU St. Louis several years ago and laid the groundwork for succeeding John. Sam Butcher is also a co-PI. And when I joined, the three of us then are sharing responsibilities through the user program that Katie leads, the technology development solid state NMR program that I lead, and Sam Butcher contributes to studies of RNAs and also works with the user program. We also have expanded greatly at Madison, and one of the major reasons I moved here is because not only in NMR, but also in cryo-electron microscopy, there have been major investments here in Madison. And Liz Wright, as you see in the upper right corner, is a PI that was recruited from Emory University. And we've hired 3 assistant professors, Tim Grant, Rob Kirchdorfer, and CJ Lim in the last 2 years, and have expanded greatly the cryo-EM capabilities in Madison. So just briefly, I would like to thank Hector DeLuca, whose patents have paid for most of this. And the 3 buildings that we work in are named after him. Brian Fox, the chair, who recruited me, Steve Ackerman, the vice chancellor for research, and Brad Schwartz, who's the CEO of the Morgridge Institute and a collaborator of mine from Illinois who moved here a few years ago. Okay, so just to point out, the cryo-EM facility is having its grand opening in June, and Liz will be hosting that big shindig. And Josh Kuhn, also, I shouldn't fail to mention, is another neighbor who has a P41 center in quantitative biology. So it's a really great environment to do science here in Madison. And we've gone through a major set of upgrades in NMR FAM. And so prior to my arrival, NMR FAM was mostly focused on solution NMR. Katie began the transition to solid state NMR, but then we wanted to double down on that in light of the advancements in proton detection, in ultra high field magnets, in DNP, as well as in carbon detection NMR. And so as part of my startup, we moved a couple magnets in. We moved a 750 wide bore existing from Illinois, and we did mostly with my startup upgrade of a number of NMR consoles and probes. Okay, we were very fortunate last year to be funded by NIH as a P41 center for development of probe technology as well as computational and sample preparation methods. We also received from NSF last July a mid-scale research infrastructure grant, which is paying for 2 1.1 gigahertz instruments, one focused on solid state NMR that will be located here in Madison, and another in solution NMR that will be located in Georgia with Art Edison. So we are developing customized probes for this project, and there's a computational infrastructure being developed at UConn by Jeff Oak, which is also where the BMRB has moved. After John's retirement, the BMRB has moved to Connecticut along with NMR Box, and the synergy there was helpful in convincing NSF to fund the mid-scale project. And then in September of last year, we received funding from NIH for an R24 for the user program. So Katie leads this user program, Jeff leads the NSF project, and I lead the technology development project. So I want to say a little bit more about the specific probes and just a few pictures here to very briefly summarize some of these efforts that happened mostly during COVID. And so Kevin Gehring was one key member, a former Agilent employee who helped move a lot of the spectrometers. We brought in 2 Oxford magnets, 1 Bruker Ultra Shield magnet, and the 750 wide bore Agilent system from Illinois. So that was craned into NMR FAM in August of 2020 and brought to field in November. And during this entire process where we energized 4 magnets during 2020, we collected over 80% of the helium in the process of energizing and shimming those magnets. And we have expanded, you can see a few of the recovery units along the east wall of NMR FAM in 3 bags. And we are liquefying as fast as we can, of course, in the context of the helium shortages. And so we're very interested in maintaining the sustainability for NMR, and in particular in maintaining a very high level of recovery, which at this point in NMR FAM is around 90%. So in 2021, we hired several new staff. A number of the staff who'd worked with John Markley retired when he did. And so we've hired a project manager, Nathan, 3 scientists at the PhD level, Thirupathy Ravula, Alex Patterson, Gopinath Tata, and I'm sorry, a 4th, Zonglin Wang, 4 PhD staff scientists. And we've also hired an information technology professional. And so that goes along with longstanding staff, Paulo, Falco Cobra, and Marco Tonelli, who really kept the ship running during COVID. So during the COVID stretch, it was amazing that Marco and Paulo almost, the two of them single-handedly ran the entire NMR fam. Okay, so on that note, there are actually two positions that are currently open, one for a research specialist and another for an applications developer, and you can find those on jobs, HR, WISC, EDU. Okay, so now to come back to the ultra high field topic, okay, we've been very pleased to see that in Europe, a number of 1.2 gigahertz and 1.1 gigahertz systems have come to field. Of course, there's a 1.1 gigahertz in Memphis, that's St. Jude. And in the US, there are 3 instruments that will be installed, we hope, in the coming year to year and a half. One is a 1.2 gigahertz shared instrument that will go to Ohio State. That was the result of a mid-scale research infrastructure 1 grant from NSF. And then our project, the Network for Advanced NMR, will deliver the 2 magnets that I already mentioned earlier. And so as part of this, we're working very closely with the University of Connecticut and Jeff's group, and as I mentioned, BMRB and NMR Box, to develop data sharing standards, cyber infrastructure to address security, automated backup, data sharing, access, and to utilize and leverage instruments that are in large facilities. Because unfortunately, due to the helium crisis, I continue to hear about magnets at individual institutions that are being de-energized because of the cost of helium. And so in larger facilities where it's possible to do the full helium recovery and take advantage of an economy of scale, we want to make sure these instruments are being utilized to the fullest extent. And by the way, the magnets in NMR fam are named after cows, and we've selected Lockenfelder as the name for the 1.1 gigahertz, and that's because it has 11 letters. We need 1 letter for every 100 megahertz. Okay, so the main point I want to talk about in the remaining time is that of probes and consoles and how we can improve C13 sensitivity. And Bob asked when I sent him the title, does this mean you're not interested in proton detection anymore? And absolutely not, that's not true. We have seen remarkable progress in proton detection, and part of that I was involved in directly, and we continue to do proton detection at NMR fam, and we look forward to getting a 0.7 millimeter Bruker probe with our 1.1 gigahertz system, and we're working to install similar probes on other systems. But in addition to proton detection, carbon detection has a lot of virtues and a lot of important applications in biological solid-state NMR. We're also, as part of this NSF project, supporting material science NMR, where low gamma detection with high sensitivity is a very high priority. Okay, so as you know, and as Bob mentioned, I've developed probes since I was in graduate school and continue to do so in collaboration with Varian, with Phoenix NMR, and now with Black Fox NMR. And so I want to tell you sort of at a high level where this is going. And this is an almost complete list of all the probes in NMR fam. One notable important detail here that I arranged upon my move is that we brought in 2 Oxford 651 actively shielded magnets, and they're both performing very nicely. Those are at Ribeye and Taurus here. And in addition, the Vosges magnet and the Jalan magnet are both the same design, okay? And so we actually have 4 different 600s, 3 of which are dedicated for solid state NMR, which are all compatible with all of these narrow bore 600 megahertz probes, okay? We have a 750 megahertz wide bore system, the one that was moved from Illinois, that we use principally for special applications such as quadruple resonance, HFXY, HXYZ. This probe is used for proton, phosphorus, carbon, nitrogen. We have a cold mass prototype from years ago, and we plan to do DNP with this instrument in the future, okay? Then we have the challenge of 900 megahertz. And when I started here, and Bob has noted, of course, one of the very important reasons to move to NMR fam is the access to higher fields, and we all know that higher fields are incredibly important for NMR sensitivity and resolution. But the question we asked, and Eric Hahn, who was the one courageous graduate student of mine who moved with me to Madison, several others graduated or switched groups, but Eric deserves the award for being the most courageous and making it through COVID, both literally and figuratively. And he has led the efforts to develop higher sensitivity C13 detection probes. So I'm telling you mostly about his thesis work in the remainder of the talk. And I would note also that some of my other students, Ben Harding in particular, and a new postdoc, Colin Gorsick, have really helped out a lot with this, as well as, of course, the NMR fam staff that I already mentioned, okay? So going back now, close to 15 years, we know that 900 megahertz relative to 500 or 750 yields great improvements in resolution, especially for carbon detected spectra. And that's because the carbon line widths are limited by residual dipolar broadenings as well as the scalar couplings. And those are, to first approximation, independent of field in an absolute sense. So as you go up in field, you get the full benefit, linear in each dimension, of improved relative resolution. You also often get additional effects of line narrowing due to truncation of the residual dipolar couplings. And this can be especially big for proton detection, but also for carbon detection, okay? So we've all known this now for many years, that going to higher field is great for sensitivity, and for resolution, excuse me, and we want to go higher. So we called this ultra high field in 2010, but of course we know this is no longer ultra high, but just high, and that the ultra fast spinners are no longer ultra fast, but just fast, and so on. So we should stick with numbers instead of adjectives, as I always like to tell my students. This is another point I'll just, the reason I show this slide here, in addition to illustrating some of the helium recovery infrastructure, is that in February of 2022, when we started setting up magnets, so I moved January 1st, 2020, we had these magnets at field about 6 weeks later, and both 600s, one at 599.3 and one at 598.7, to go along the others that are about 0.5 megahertz apart. And we used an Infinity Plus console that I moved from Illinois that was manufactured in 2002. And it, as of February 2022, still had a 1 dB noise figure on the carbon channel. And it had better signal noise than the 3.2 millimeter probe on the 900 megahertz Bruker system, okay? So we were very interested in understanding how we could address that, because we weren't receiving any of the benefits of higher field in terms of sensitivity, although we were getting the resolution benefits, okay? So this is where my long-standing collaboration with John Stringer and his team at Phoenix NMR comes in. And so there's John on the slopes of the ski slopes in Colorado with his wife Sherry, after they successfully built and shipped out my PMAS controller and my probe in the middle of COVID, okay? So they were shut down. His daughter Alanis and his son Jacob helped build the PMAS controller and to finish the ship out of the probe. And we received that probe just before we went on total lockdown for April of 2020, okay? So when we returned in early May, I worked on installing that probe. And Paulo and Marco and Kelsey Collier, who I should mention, a former student from Rachel Martin's group, were really the only ones with me in NMR FAM. It was a very socially distanced magnetic environment. And we were testing this 1.6 millimeter probe from Phoenix NMR. As you know, it's really helpful that the Phoenix probes have this design that allows the probe head to be removed, so we can compare the performance of different resonators, different module sizes, different rotor sizes. So here's the magnet, the probe underneath the 900 magnet at NMR FAM, and it's integrated with a Bruker preamplifier, a Bruker Avance 3 console, and the VT, which exhausts through the top of the magnet, goes to -50, and the spinning goes up to 40 kilohertz, okay? So we also, for comparison, had started a few years ago before leaving Illinois on designing a hybrid probe that would use Peter Gorkoff's loop gap resonator solenoid dual resonator design, along with a Phoenix NMR spinner. Okay, so we built a 600 megahertz version of that in collaboration with Phoenix NMR a few years ago. And this is the second iteration, which is a 1.6 millimeter Phoenix head on top of a Black Fox NMR probe that is optimized for carbon detection. Okay, so the question here is purely, can we take Peter's resonator technology, combine it with the Phoenix spinner technology, and give an optimal performance in terms of resolution and sensitivity at 900 megahertz, okay? So as you know, Holt and Richards defined, when I was in kindergarten, the equations that govern the signal noise improvement with field strength. And there's prefactors, and if you're assuming you're working with carbon, you have a magnetic field dependence, you have a spectrometer dependence built into the noise figure of the receiver, you have a dependence that's purely on the probe in terms of the coil Q and the filling factor, and then a factor that depends upon the sample. And if all of this is working perfectly, you can hope for B0 to the 7/4 power, okay? In practice, there's a lot of contributions that for a solid state NMR impact the signal noise that are often very hard to keep track of and quantify, okay? And one of the reasons Eric has gone through this extensive study is so that we at NMR FAM as a research resource can provide standards for the community, as well as protocols that are reproducible to measure signal noise as a function of field, okay? So when we consider not just the magnetic field strength, but also the shimming and the homogeneity and the drift, That is important, as well as the console performance, particularly the amplifier stability, the receiver preamplifier, receiver performance in terms of noise figure, the probe itself, as we'll say more about, and then the pulse sequences that you use. So if you're going to do a systematic analysis of signal noise, you have to separate these factors. You can't just lump them all together, because then you can't see the trends and properly correct and improve the design, okay? So there's some builds here, which I don't need. All right, so that's repeating, but I would say, so for amplifier performance, let me just make one comment about that. We had reheat valves in NMR FAM that were controlling the temperature of the main room, which worked reasonably well, but when we replaced those with variable voltage controlled reheat valves from Jensen Controls, I'd recommend you talk to your steam fitters and see if you can find those in your, and install them into your system, because now over the last month around the 900 magnet, the temperature has ranged from 71.2 Fahrenheit to 69.8 Fahrenheit. And this little difference of about a ½ degree Fahrenheit came from the fact that the weather warmed up and they filled the coils with chilled water instead of using outdoor cold air, okay? So for literally a month, we can maintain temperature within plus or minus 1 degree Fahrenheit. And if you put it in Celsius, it sounds even better, okay? So that's a really important part for getting consistent sensitivity and reducing T1 noise in multidimensional experiments. The other piece of the hardware that's absolutely essential to maintain, to achieve optimal signal noise is the front end preamplifier, okay? And so some preamplifiers, in particular, we noted on the 900 megahertz system, this preamplifier has a noise figure of about 3 dB on the carbon channel. We were able to improve it to about 1.8 by adjusting some of the cabling and replacing the second gain stage with an ARR low noise preamp, but it's still at 1.8, which is not as low as we would like, okay? So we're in the process of making compatible with the Bruker system the front ends that we first developed, and Bob knows very well from MIT with Warner Harrison. We first developed these, and Chris Juronic did some beautiful experiments with selective read-or, because these were low noise figure, high power, and they were perfectly linear from microwatt to kilowatt range. So for soft pulses on carbon, this is really essential. We, with Warner, when I was at Illinois, advanced this front end to get us compatibility with the Varian system. We then worked with Varian to develop a broadband version of it. This is the X-channel high power actively switched broadband preamplifier. And so clearly the advantage here is that you can replace the quarter lambda with a low loss cable. You can achieve a noise figure of 1.0 to 1.2 dB over a very large frequency range. And so that delivers a noise figure about 1.1 to 1.2 dB at 600 or 750 megahertz for carbon. Okay, so 150 or 188. At the 226 on the carbon frequency of the 900, we're still not quite there, all right? So briefly, just to say, the other issue that has come up in this project is when we look at standard compounds, there's a lot of inconsistency in the literature. Many of us use adamantane to shim, and you can nicely see, as Kurt Zilm taught us years ago, how to resolve the natural abundant satellites there in adamantane, so you get beautiful line shape, but the signal noise in adamantane depends almost entirely on how well you shim, so that's not a great standard to use for signal noise. Hexamethylbenzene has some unfortunate relaxation properties and is hard to cross-polarize, and so although it's a nice challenge for low field, doesn't work out so well for high field. Glycine, likewise, has a challenge with decoupling. It depends on magic angle, it depends on how well you decouple, and it also has a very long proton T1. So there are a few different solutions for this. One that we prefer at present is NAV and acetylvaline, and the rationale is that this has a short T1. It has different sets of carbons, some methyls, some methynes, carbonyl. It also can be made either at natural abundance or labeled relatively easily. And Stan Opella showed us how to crystallize that about 20 or 30 years ago, okay? So I think I already said all that. And so then the additional issue to take into account is how you evaluate the noise floor, okay? And I'll skip some of these technical details, but this will be in a paper that Eric is ready for submitting now. When you look at the noise floor in a solid state NMR spectrum, of course, there's dependence on the filter settings. There's dependence in particular in the Bruker and the digital filter settings. And there's also potential that you could see very small impurities and or sidebands that would be misinterpreted as noise, okay? So this build isn't helping me either. But here, for example, is the spectrum of NAD where you see the sidebands of the methyl groups, and you can see second order sidebands of other resonances. And so if you're not really careful about where you select the noise region, you can get misleading results. And so we have a practice of started measuring noise as a separate spectrum, also comparing that with the noise in the detected spectrum and performing statistics to confirm that we're getting reliable measurements. And now we can measure the signal to noise to within a few percent. And that is almost always limited by how well you can measure the noise, not the signal, okay? So that gives us a 2.5-fold improvement in the measurement precision when we follow that protocol, okay? So now I'll just very quickly go through a few examples, and here Eric has prepared several slides where we look at the theoretical improvement that we expect and compare that with the actual improvement, okay? And so when you go from triple resonance mode to double resonance mode at 600 megahertz, for example, you would expect to get about a square root of 2 or factor 1.5 improvement due to probe efficiency, and we see that. If you perform cross-polarization, you'd expect to see a factor of 3.5 to 4, and we see that at 600 megahertz, okay? When you go from 600 megahertz to 750 megahertz, you would again expect the 7/4 dependence, 750 over 600 to the 7/4 is 1.48, and so therefore it'd be 1.5. And within error, we get that once we correct for the difference in the noise figure of those preamplifiers, okay? What you start to notice, however, is that when you do cross-polarization, you don't quite get as much of that signal noise benefit. You still get close if you're using, for example, a Balun design or a biomass design with a scroll resonator or balanced solenoid. Kurt Zilm has shown us this in other contexts at 800 megahertz, where to maintain full CP enhancement at 750, 800 and above, you really need to think carefully about the resonator design, okay? So there's some other dependencies which I'm going to skip over in the interest of time, but I would point out that the Phoenix probe with a solenoid unbalanced results in only a slight increase in signal noise when we go from 750 megahertz to 900 megahertz, okay? So we don't quite get the theoretical improvement of 1.38, and this is taking into account the efficiency of the circuit, the noise figure, and so on. So we're losing about 15%, relatively speaking, even for the methyl groups, in terms of cross-polarization efficiency, okay? Or in terms of, in terms of the B1 homogeneity on the carbon channel. Now, when we go to cross-polarization, we actually lose signal noise. When we go from 750 to 900 with the same rotor within a few percent of mass, and we see that the signal noise actually goes down, okay? And of course, the reason for that is because in an unbalanced solenoid, you have B1 inhomogeneity that starts to become a serious issue for cross-polarization. And so what's shown here is if you put a magic angle, a gradient along the axis, which is just an adjustment of the Z1 and X shims, you can broaden those methyl groups and see a coil image, and then you can do a nutation curve, and you can see that the nutation actually on, and I have Maya's in my way here, so I have to move this out of my way on my screen. The carbon nutation curve and the proton nutation curve have maxima on different sides of the coil, or maximal homogeneity on different sides, because the coil has a ground for proton on the top and a ground for carbon on the bottom, okay? So this results in a suboptimal CP enhancement, right? So you can see the numbers there, and we can come back to that if you're interested in the details. But now with the Gorkoff design, we're able to achieve much higher B1 homogeneity, okay? So the 810/90 is about 84% for proton. It's a little bit better, or, I'm sorry, this is for carbon, but we're getting a similar homogeneity for proton. And most importantly, there's a very good field overlap between those two channels, okay? So now when we go from the 750 fast mass probe to the Black Fox probe, in terms of the direct polarization signal, we see better than the theoretical enhancement, because even at 750, the carbon homogeneity is costing us some. And so we gain back that. And then when we do cross-polarization, we get a full factor of 2 better signal noise when we compare 750 to 900, okay? And this is actually with the HCN mode, so there's a correction factor there we applied. But the bottom line is that we're getting a signal noise that's 1600 to 1 in the labeled sample. And I think the next question would be, if you go back to natural abundance, how do those numbers come out in summary? And that is, you see about 270 to 1 according to this approach with the methyl groups of NAB. At 600 megahertz, you get up to 420 to 1 at 750 and 430 to 1 at 900, where notably these best effort numbers here are with a full 3.2 millimeter rotor in the case of 750 in double resonance mode, and a 1.6 millimeter rotor in triple resonance mode at 900. So the mass limited sensitivity, or if you correct for the number of moles of material in the rotor, you're getting almost a full factor of 2 better sensitivity going from 750 to 900. And that's even if you're using the 3.2 millimeter probe at 750, okay? And so to wrap this up, I would say that this is an example of a membrane protein spectrum collected with that 900 megahertz probe. This is carbon detected. It's a standard we're using in the lab that Mei Hong has also published some very beautiful work on with Katie Hunser-Wildman recently. It's EMRE, it's about 50 nanomoles effectively of material, and we can collect a 500 millisecond DAR spectrum in about a day and a half and see a lot of the weak cross peaks. The shorter mixing time spectra can be collected in a couple hours. And we recently had a user who was trying to get data with a 3.2 millimeter rotor at 600 megahertz. And we actually transferred that material from the 3.2 millimeter rotor to the 1.6 and brought it to the 900. And we're able to collect the data approximately 5 times faster with half the material, okay? So that's all I have to say. I appreciate your attention. And I would just say again, we have jobs here in Madison. This is the view from my back porch. This is my son Nicholas and I at the Rose Bowl in 2020. This is us at the Ryder Cup last year. This is my NMR FAM license plate. And I would point out finally in closing for Bob that, you know, Cambridge is really just a small village east of Madison. It's a suburb of Madison. And it was unfortunate, but for many months over the last year, the ramp to Cambridge was closed while the exit to Madison was open. So with that, I appreciate your attention. I'd be happy to answer questions.
Okay, well, thank you for a very illuminating talk, per usual, Chad. Lots of interesting new bits and pieces of information. Okay, so there are already, let me see, a couple of questions here. Joanna Long says, this is a comment rather than a question. Black Fox is a spinoff of the NSF-funded NHMFL laboratory. The designs and details and development are published, she says, okay?
Yes, indeed. Thanks, Joanna. I appreciate that. And you're right that, and I should have made reference to the earlier paper. So thank you for reminding me of that. And yes, what we've worked on with Peter and Phoenix is trying to adapt those technologies to different spinner geometries. But the earlier technology was developed at NHFML. Thanks.
And Wenhei Lee said, Chad, this is a great solid state NMR hardware accomplishment at NMR FAM. Please clarify NMR FAM's accomplishments and plans for the software development under the current P41, since this is TR&D 3, and you briefly brought that up in the beginning of your talk.
Okay, yeah, that's really a whole separate talk, but I think the if I go back just one moment, please, I would point out that, well, here we go. This is the slide that would summarize this idea. Is that, you know, so Tim Grant is a new assistant professor here in Madison who is working in the cryo-EM facility. Tim is the project lead for TR&D 3 of the P41. And Tim's expertise is in development of cryo-EM data and image processing. So he developed, while a postdoc with Nicholas Grigoriev at Janelia Farm, the program called System, which is one of the leading programs for doing particle picking and analysis. And he is working on extending cryo-EM methods to small proteins. And small to Tim is tends to maybe 100 kilodaltons, which is what we think of in solid state NMR as pretty large. And so Tim and Katie and I, along with a number of the NMR FAM users and driving biomedical projects, are working on joint refinements of membrane protein and fibril structures using a combination of solution NMR, solid state NMR, and cryo-electron microscopy.
Okay, Wan Hong Lee says, thanks, Chad, for the clarification. I really needed that. I hope Oswego University Ridge in the near future. I'm not sure what that university.
That's the best golf course in the Madison area, and I welcome you, Woong Hee, to visit, and I'd love to go out and golf with you. Other questions? So
you're spinning at somewhat modest spinning frequencies these days still. I noticed the number 13.333 kilohertz for 3.
Correct, yes.
What are you going to do about that as you go to higher fields? Okay, so I mean.
Excellent question, yes. Okay, so let me show you some sidebands, Bob. I love sidebands. Let me find those again. We showed the sidebands at high signal noise somewhere in here. Okay, so yeah, you have sidebands. Can you see that?
Right.
Our sidebands here are parked, those are the sidebands of the methyls, which are usually so weak you wouldn't see them. That would partially overlap with the aromatics. And, I think Ann and Kurt, among others, Hartmut, years ago when the spinning rates were more limited, found that parking that first order carbonyl sideband around 85 to 90 ppm would result in a situation where the second order carbonyl sideband is out here at 0. And then you do have a disadvantage that there is some overlap of the aromatic gamma carbon cross peaks with the beta carbon region. So there's a few issues of that sort, okay? So that 13.333 kilohertz is equivalent to 88.8 ppm carbon and would park the sidebands in that manner. You are correct that if you're at a 1.6 millimeter rotor geometry, at 600 megahertz, we actually prefer to spin at 26.6 kilohertz, right? So that would put the first order carbonyl sideband over here, and it would put the aromatic sidebands out of the window, okay? So now if you scale up that 26 kilohertz, you scale the 13 kilohertz up to 900, that translates to 20 kilohertz. And so we can just barely make it 40 kilohertz at 900. That's again, consistent with 1.6. But we think we might be able to get better sensitivity with a 2.5 millimeter rotor, which has double the volume and can also spin at 20 kilohertz, right? So we're interested in these two different scenarios, one in which you're spinning at that 88 ppm range, another one where you're spinning at 170 plus ppm. And so then, depending on what you do, you may have some sidebands to deal with. But if you're not mass limited, we think you can get double the sensitivity by, for example, using the 2.5 millimeter rotor at 900 megahertz. Now at 1.1, we have to go up another 20% roughly in spinning rate. So that would put us around 25 kilohertz or 50 kilohertz, right? So at 25 kilohertz, you could still use the 2.5 millimeter Phoenix geometry, or Bruker has some similar products like a 1.9 millimeter that would meet that specification. But to go to 50 kilohertz for carbon detection implies a major compromise in sample volume. And so it remains to be determined when we go to 1.1, whether we're better off with the 25 kilohertz or the 50 kilohertz. But we have probes on order so that we can do both of those. And in particular with the Phoenix design, it's very helpful that we have a 1.2, 1.6, and 2.5 millimeter all that we can interchange, and we can evaluate that in more detail at high field.
No, the Phoenix, the flexibility to change the stator is really, that's a big.
It's a very flexible probe. It's a workhorse probe. Those tune also in narrow bore HFXY, which is a special capability I don't think is offered elsewhere. And for material science, where NSF was very concerned about how we would meet the demands of many material science users. And unfortunately, Bruker was not able to quote us a probe that had broadband tunability at 1.1 gigahertz. So we in that situation really need to rely upon the technology from Phoenix NMR to give us broadband tunability for the material science community.
Okay.
So Bob, can I ask a question?
Sure, Art, go ahead.
Chad, I have two. The first is will just require a quick comment from you. Do you want to say anything about your prototype cryomass probe? But the question more related to your talk is usually when I teach students, I tell them sensitivity goes kind of gamma to the 5/2, and you said 7/4, which differs by a square root of 2. So where does that square root of 2 come from?
So, well, I would say the 7/4 is from Holton Richards. Let's go back to that equation, because I think I'm going to lean on Holton Richards and the data we have for carbon if you're within the same nucleus. Okay, so you get one factor from Boltzmann. Okay, you get a square root of frequency for induction because the voltage is larger, but the induction factor goes down by square root of frequency. And then you get a quarter power and quality factor, assuming that your Q is proportional to the square root of frequency, which it should be if it's well designed, right? So that gives me a 7-force limit. Where do you get the other factors from?
Well, I'll have to go back to this reference and compare it then to what we say in Cavanagh et al.
Okay.
So thanks for this reference.
All right. We'll follow up with you on that. And the question about the cryomass probe, I think I wouldn't have a whole lot to say about it other than it was an early prototype, which has now been improved, and Phoenix has a commercial product with that latest design, which is compatible with wide bore up to 750 or 800, which is as high a wide bore magnet that you can get, right? And they're also working on bringing that down to narrow bore geometry. So I think I would defer to that for the moment.
Art, I had the same question, but maybe we can discuss it further in the informal session after the talk, because probably we should switch now to the.
Okay, wonderful. And I'll try to answer the questions in the chat if there are more. Okay, thank you.
Okay, so shall I introduce the next speaker? Yeah. So it's a great pleasure for me to introduce Malene. So I've known Malene for nearly 25 years. It sounds like a lot, but it's been good. Where we started to study as a chemistry at the University of Copenhagen. Now, as Malene then went on, and as we did a PhD with as Jensen, the late Jensen, whereas Malene studied a lot of as a paramagnetic proteins. He did a great job developing a lot of techniques there. Now, from that, as Malene moved to France, moved to as Martin Blackledge's group, and started to look at as IDPs, and in particular use as RDCs to probe these IDPs. And also, again, he did he has a great job using NMR and also some computational tools. In 2010, Malene got a CNRS position to stay in France, in Grenoble. And as he continued with IDPs, and really I'm sure that most of you know of her papers, whereas not only as using RDCs, but also as other constraint could really start to see the energy landscape of IDPs and also how they bind to various binding partners. Now, for that, she got a prize, the CNRS, as a bronze medal, very well deserved, of course. Now, Malene is now as a team leader. Her group is as NMR and as a signaling complexes, I think it's called. Malene, correct me if I'm wrong. And she's now broadened more out to study like kinases and others biologically sort of very important complexes. And as you will see, I think from her talk today, is the unique thing about Malene is she really manages to tap into all the different areas of as a solution in NMR. Started in a paramagnetics, have done RDCs, and also sort of as microsecond, millisecond exchange. And I think we're going to see a very nice and beautiful example today. So as Malene, please go ahead.
Thank you, Fleming, for this nice introduction, and also thank you to the organizers for inviting me. Yeah, so I'm going to present our work on visualizing protein breathing motions associated with aromatic ring flipping. So first of all, aromatic residues, they really make up a significant fraction of the hydrophobic core of folded proteins. And in the hydrophobic core, they often engage in different types of interactions. So for example, CH-pi interactions, cation-pi interactions, pi-pi, as well as hydrogen bonding. So they're really essential in many cases to maintaining the protein fold and stability. And the topic of the presentation is aromatic ring flipping, and I'm sure you all know about it as NMR spectroscopists, but for those of you who don't, I will just say that it's a rotation of 180 degrees around the Chi2 dihedral angle, so there is essentially no difference in the conformation before and after a ring flipping event. So of course, how do we know that this occurs? And this is one of the beautiful examples from NMR studies that were carried out in the 1970s. where it was shown by, among other people, Kurt Wüthrich, that exchanged averaging of the NMR signals corresponding to the 2 delta protons and the 2 epsilon protons were occurring in assigned NMR spectra of these aromatic rings, meaning essentially that the ring flipping is either fast or on an intermediate fast timescale. What was even more surprising potentially was that aromatic ring flipping was shown to actually occur in the hydrophobic core of proteins. So why is this surprising? Well, first of all, as I just said, aromatic rings in the hydrophobic core, they usually engage in different types of interactions to maintain the protein fold. And these interactions would have to be temporarily broken for the aromatic ring flipping event to take place. Second of all, if you look at high resolution crystal structures or also NMR structures, what you see is that the hydrophobic core in many cases are very tightly packed, and there's most of the time not really space for the aromatic ring to pass through the 90-degree angle. And this was also realized very early on, and I took a quote here also from an article in the 70s, where they stated that it may be necessary to invoke some sort of breathing motion in the protein to allow this proposed flipping process to take place. And of course, there's been a lot of many different NMR studies since then on aromatic ring flipping, in particular from different NMR groups. And in many of these studies, ring flipping rates have been measured as function of temperature and pressure to derive activation energies and volumes. And in particular, the volume I find very interesting. So the volume would be the volume that needs to be generated around the ring, so that is related to these protein breathing motions in order for the ring flipping process to take place. So this we have somehow a quantitative measure of, and I will come back to this. However, what was lacking somewhat at this point was to elucidate the structural details of these proposed breathing motions. So what are the structural rearrangements that would be necessary in order to generate these activation volumes and thereby enough space for the aromatic rings to rotate? Okay, so we were looking into this. So the model system that we are studying is an SS3 domain. So of course, it's a small protein of about 60 amino acids. And we could show by NMR, when we started to study this, we realized there was a lot of conformational exchange in this protein. So this you see down here, where we measured CPMG relaxation dispersion experiments, both on nitrogen and proton. And here I have plotted the exchange contributions to the transverse relaxation. And there was really a lot of exchange in this protein. And so when we analyzed this, we could see that this protein populates 2 different states in solution, a major state, which is here named state A, populated to 97.3%, corresponding to the crystal structure that was determined previously of this protein, and then a minor state populated to 2.7% with a structure, of course, that is different to the major state. And we could determine the forward and the backboard rate constant between these states through analysis of the CPMG relaxation dispersion data. And of course, as NMR is a very powerful tool, we have very specific insights, and we could see which residues are specifically affected by this exchange. And they are the ones that you see here. They affect around 40% of the residues. And when we map that onto the structure, we could see that all of these residues essentially cluster around a tyrosine that is located in the hydrophobic core of the protein, namely tyrosine 526. So when we mutated this tyrosine and we repeated the relaxation dispersion experiments, basically all of the conformational exchange was abolished. And we revert to an energy diagram where we have a single state in solution, so populated to 100%. So of course, there may be many reasons why you abolish conformational exchange when you start making mutants. And one of them could, for example, be protein unfolding. And so of course, we checked this both by NMR, but we also determined the high resolution crystal structure of this mutant, and we compared it to the wild type. And as you can see here, there's essentially no structural difference, except for a slight reorientation of some side chains in the vicinity of the mutation site. So what this tells us is that this tyrosine mutant is really the origin of this observed conformational exchange. So how can this tyrosine, so what is so special about this tyrosine that is located in the hydrophobic core? Well, first of all, it is found in a very unusual conformation. So the Chi2 dihedral angle, as you see here in the Newman projection, is at 2 degrees. So this means that you often have steric interactions between the delta 1 nuclei of the aromatic ring and the protein backbone. So it's not at all a favorable conformation. And this is, of course, also confirmed when you look at the distribution of tyrosine Chi2 dihedral angles in PDB structures. You see here an angle around 0 degrees is really very rare. So somehow this unfavorable conformation must be stabilized by something in the structure. And it turns out that when you look at the structure, it's really stabilized by several CH-pi interactions from alanine 541, Q520, and valine 517, and then pi-pi interactions with the nearby histidine 493. So we wanted to understand a bit more in detail how the nature of these surrounding amino acids affect the conformation of this central tyrosine 526. So in order to do this, we retrieved the sequences of 320 human SS3 domains, and we carried out a sequence alignment. Then we retained only the SS3 domains that carry a central tyrosine or phenylalanine at the position of tyrosine 526 in our GIP1 SS3 domain. So this amounts to 33 SS3 domain, and then we looked at the amino acid distribution in the 4 surrounding positions, and we color-coded them according to the number of heavy atoms in their side chain, so basically the size of the side chain. As you can see, there is a large distribution both in position 541 down here, and also in the position of histidine 493, and to a smaller extent in the 2 other positions. So in order to understand whether there is really any size correlation between these different amino acids in these different positions surrounding the ring, we carried out a principal component analysis using as input the number of heavy atoms in the side chains in these different positions. And it turns out when we do this that the 33 SS3 domains cluster into 2 different groups. Group 1, where we find the GIP1 SS3 domain, and we already saw that this is characterized by what we call a Chi2 eclipse conformation. So this is the Chi2 dihedral angle of 2 degrees, where the carbon delta 1 and the carbon alpha are very close together. So this is what we call in this case a Chi2 eclipse conformation. In group 2, we find 5 SS3 domains for which high resolution structures were solved previously and deposited in the PDB database. And interestingly, all of these structures have a staggered conformation with Chi2 dihedral angles between 60 and 80 degrees. At this point, we then hypothesized that group 1 SS3 domains are probably eclipse conformations, and group 2 SS3 domains are staggered conformations of the central phenylalanine or tyrosine residue. So in order to support this hypothesis, we identified 2 SS3 domains of a scaffold protein called POSH, where the first SS3 domain are in group 2 and the 4th SS3 domain are in group 1, is in group 1. And we determined the high resolution crystal structures of these 2 SS3 domains, and in agreement with our hypothesis, the 4th SS3 domain of POSH is in an eclipse conformation of the central phenylalanine, as you see here, whereas the first SS3 domain is indeed in a staggered conformation, in agreement with the other structures that were solved previously. At this point, again, we made another hypothesis, that is that actually the minor state that we observed of this GIP1 SS3 domain is actually corresponding to a group 2-like structure. So we would essentially have exchange between group 1 and a group 2 structure. So we set out to try and stabilize the minor state, so the group 2 structure, by introducing single point mutations. And for this, the results of the principal component analysis they're really valuable, because we get basically the characteristics of the amino acids in the different positions surrounding the aromatic ring. So here you see in group 1 on the left and group 2 on the right, and the sizes of the spheres here correspond to the arid size of the amino acids in these surrounding positions in group 1 and group 2 structures. So first of all, we looked at the position 541, and we see that larger side chains over here would favor a staggered conformation. So we designed a point mutation, alanine 541L. Also in position 493, we see that smaller amino acids would favor a staggered conformation. So we designed the mutation histidine 493 alanine. And we also see that in position 517, isoleucine or leucine is really very abundant compared to only valine in the eclipse conformation. So we made a V517L mutation, and we added a, let's say, an independent mutation, which has really nothing to do with the principal component analysis, but it's the V517A mutation that serves the purpose of, let's say, increasing space above the eclipsed ring here for the transition to the staggered conformation. So in order to understand whether these mutations are actually doing the job, let's say transitioning to a staggered conformation, we solve their high resolution crystal structures. So here in the center, you have the wild type conformation, and here on the top here, we have the structure of the V517L mutation. And as you can see, this is really not helpful. It didn't do anything to the structure, and we are still stuck in the eclipse conformation with a chi-2-dihedral angle of 2 degrees. When we move on to the alanine 541L mutation, we indeed managed to induce a staggered conformation of the tyrosine 526 with a chi-2-dihedral angle of about 70 degrees. And we see that this staggered conformation is stabilized by CH-pi interaction with alanine 521. And you see some structural changes in this beta strand here surrounding the ring. What was then really surprising was that when we looked at the structure of the V517 to alanine mutant, we again have a staggered conformation, which is stabilized by leucine 519. But as you can see that the structure is different to the one that we get when we look at the A541L mutant. And again, when we look at the histidine 493A mutant, we were again successful in inducing the staggered conformation with a stabilization mechanism that is identical to the one that we observed for the V517A mutant. So at this point, we don't really know if any of these structures are representative of the minor state that we see by relaxation dispersion in the wild type protein. So basically we have two different candidate structures. So we have the A541L structure, where we basically have a looping out of this beta strand, or we have the histidine 493A, V517A structures, which are identical, but that have a different stabilization mechanism. So in order to understand which of these structures would correspond to the minor state that we detect by relaxation dispersion, we used NMR, of course, and we studied first these two different mutants here by solution NMR. And first of all, what we saw that when we started recording HSQC spectra of the wild type and compared them to the two mutants, what we saw was that for a subset of residues, we see a linear correlation of the chemical shifts. What this means is that we have fast intermediate exchange between two different structures for these mutants, the two structures corresponding to what we have for the wild type SS3 domain, and of course the structure that we determined for these two different variants. We also measured relaxation dispersion for these two different variants. So they are definitely still in conformational exchange between two conformations. So we're not able to fully populate the minor state using these mutations. And using these data, so comparing the chemical shift differences between the two states that we can extract from relaxation dispersion for the mutants and the wild type protein, we can compare those, and you can see that we actually have a nice agreement between these two data sets. So this means that the structures that we determined by crystallography of these two mutants actually represent the minor state conformation that we detect by relaxation dispersion in the wild type protein. What is also interesting, and what we see from when we start to do the solution NMR experiments, is that actually the histidine 493A peaks are always very close to the wild type. So of course, the degree of shifts along this line here gives you an idea about the population between the wild type conformation, or let's say the major state conformation, and the minor state conformation. So we can, from this, we can derive how much we are in eclipsed and staggered conformations. And of course, what is interesting here is that for the histidine mutation, we're actually only managing to stabilize the staggered conformation by about 7% compared to the wild type protein. And yet this is the form that is captured by crystallography. For the valine 517-A mutant, we are able to almost inverting, or we are really able to invert the conformational NLE landscape and stabilizing the staggered conformation to 89% compared to 11% for the eclipse conformation. So now we know what is the structure of the major state. So this was the structure that was determined previously, and we know what the structure is of the minor states corresponding to the structure of these two histidine and valine mutations. But what are the actual structural changes? So the main change is in a beta strand in between residue 517 to 523. And what you see in the wild type protein, so the major state, is that this beta sheet here has a classic beta bulge at position 518. So you see essentially you have two carbonyls pointing outwards, consecutive carbonyls. This is replaced by a canonical beta strand in the two mutations. So we have a transition here between the classic beta bulge to a canonical beta strand. And of course, in the canonical beta strand, we have the typical in-out, in-out, in-out pattern of the carbonyls. So this transition going from the beta bulge to the canonical beta strand is exactly what allows leucine 519 to come in and stabilize the staggered conformation of the ring here, because in the major state, this side chain is actually solvent exposed. So this transition really allows to stabilize the staggered conformation using this incoming leucine 519. So here is a video that shows the transition between the major and the minor state for this protein. So here in the major state, you have the eclipsed conformation of the ring that is stabilized by multiple CH-pi interaction and pi-pi interactions with the nearby histidine. And then you have the beta bulge to the beta strand interconversion that allows leucine 519 to come in and stabilize the staggered conformation of the ring. And there is also some CH-pi interactions of this leucine with another tyrosine that is tyrosine 524. And then we have the back conversion to the major state. So of course, there appears to be some resemblance. So what we're doing here is essentially a transition between two different chi-2-dihedral angles going from 0 degrees to about 70 degrees. So of course, this somehow could be related to aromatic ring flipping, but at this point, we didn't really know. So the question is, in order to answer really if there is a relationship between the formation of this minor state and aromatic ring flipping, of course, we need to first quantify the ring flipping rate of this central tyrosine. And first, we started out by recording carbon-13 HSQC spectra. So here you see the epsilon proton-carbon correlations for the 5 tyrosines in this protein. And you see that they are really, we see only exchanged arid signals. So there is no indication of observation of the epsilon-1 and the epsilon-2 protons or carbons. So what this means is that for all of the tyrosines, we have relatively fast aromatic ring flipping, including for this tyrosine 526. We next made a sample of the SS3 domain where all the tyrosines are site selectively labeled with carbon-13 at the epsilon positions. And this allows us to exploit some of the experiments that were developed by Mikael Agge and co-workers for quantifying or for measuring dynamics directly on the aromatic ring. So in this case, we would expect 2 different exchange processes to be visualized or to be observable in these experiments. First of all, of course, the transition between or the exchange between the major and the minor state, but also the exchange between the ring flip state. So the rotation of 180 degrees, of course, assuming that the 2 carbons on either side of the ring have different chemical shifts. And so we measured carbon-13 CPMG relaxation dispersion on these carbon epsilon positions, as well as on resonance R1 row experiments. And basically what we could tell was that within the experimental area of our measurements, the ring flipping process did not contribute to the experimental data. So when we analyzed the data, we basically could only see the process corresponding to the exchange between the major and the minor state. This allows us to say that the ring flipping rate is probably actually very fast, faster than what we can detect by these experiments. And of course, what we can detect is the fastest we can detect is this on-resonance R1 row. So we estimate the ring flipping rate to be faster than 50,000 times per second. Of course, this is surprising also because we have all of these different interactions that maintain the ring in this eclipse conformation. So how can we now understand this? So we have the exchange between the major and the minor state, which occurs about 2,600 times per second. And at the same time, we have the fast ring flipping probably occurring faster than 50,000 times per second. So how can is there some kind of relationship between the two? Or how can we reconcile this? And the answer sort of came when we started to look at the pocket volume of this tyrosine 526. So here I show you the volume of the pocket along the structural trajectory between the major and the minor state. So initially we have a very large increase in the pocket volume. So this is when the structural transition starts to happen. And then there is a sharp decrease in the pocket volume and a sort of a compaction of the pocket when we enter the minor state, and leucine 519 enters the pocket to stabilize the staggered conformation of the ring. This initial increase here amounts to 65 angstrom cubed, which corresponds very well to what have been measured previously for activation volumes of ring flipping events in the hydrophobic core of other proteins using pressure-dependent NMR. So their values between, as far as I remember, between 40 and around 85 angstrom cubed were necessary for allowing ring flipping to take place. So basically what we propose here is that the initial increase here is what would be the breathing motions that allow this fast aromatic ring flipping to take place, and that is what will lower the transition state energy of ring flipping at this point. So this is sort of a summary of what I just said. So again, here you have the major state on the left, either surface representation or cartoon representation, and the minor state on the right. And initially what is happening is that you have a void volume that is generated through the structural transition, mainly involving Q520 that opens up, and the pocket will have a larger volume. And at this point, we will have fast aromatic ring flipping. This will happen on a fast NMR exchange or a fast NMR timescale. So we imagine we have a continuous opening and closing of this pocket, and this is what allows the fast aromatic ring flipping to take place. Then, very rarely, we have a completion of the beta balls to the canonical beta strand transition, and leucine 519 can come in and trap the tyrosine 526 in the staggered conformation. So this is what we observe by relaxation dispersion. And of course, the fact that we were able to detect this minor state by NMR spectroscopy and eventually obtain its structure, this allows us to inform about what are the breathing motions along this structural trajectory that allows the ring flipping to take place. I would like just before the end here to come back to a mutant that we sort of discarded in the very beginning. So this was the alanine 541L. I didn't talk much about it, but it is actually a quite interesting mutant. First of all, we could show by NMR that indeed this conformation does not correspond to the minor state. So only these two conformations here, or this conformation represented by these two mutants, actually corresponds to the minor state. However, what is happening in this mutant is that there is essentially the beta strand here on the side is looping out, okay? And the reason why this mutant can probably not make the same conformation as these two other mutants here is the fact that we introduced this leucine 541 down here at the bottom of the ring, and this would sort of create a steric clash if the leucine 519 would come in. So there is sort of a solution to this problem, and that is the alanine 521. So it adopts a different conformation that is compatible with this introduced leucine 541. Yet when we start to look at the, let's say, the interconversion, or we take the structural trajectory between the major state and, let's say, a minor state represented by this alanine 541L mutant, what we observe is that we have exactly the same initial void volume being generated. And when we look at, compare the, let's say, the initial or the intermediate structures here, both for this alanine 541L mutant and the other two mutants, you see that it really resembles very well the two structures. So it means that the initial opening, all of the mutants actually report on the same initial opening of the pocket, and these are really the breathing motions that allow the fast ring flipping to take place. Then the stabilization, or the, let's say, the trapping of the ring in the staggered conformation in this mutant and compared to these two mutants is just different. But all of the mutants really report on the same breathing motions. So this is just kind of the last summary. So this is just the breathing motions in surface representation that allow the ring flipping to take place. So this doesn't transition to the minor state, but this is an opening of the pocket to the maximum volume, and then this is what allows the ring flipping to take place. And of course, depending on the time scale this opening occurs on, because we don't really have the actual rate for that. We just know it's in fast exchange on the NMR chemical shift time scale. We can have more, we can have fewer or more events. And last but not least, I would like to thank all the people who contributed to this work. So first of all, two of my postdocs, Laura and Luisa. In particular, Laura, who really did a large amount. She did all of the NMR work and most of the crystal structures. Luisa also did the POSH crystal structures. Jaka was a PhD student of mine who did some of the very initial experiments on the SS3 domain. Damien made some of the samples also for crystallography. And of course, Nicola and Martin, they contributed MD simulations that I didn't have time to include. And then, of course, I owe a huge thanks to the crystallographers, Andres Palencia and Francesco Ilassi, who's basically solved all of the crystal structures, which I think in the end amounted to about 10 or so. And we had really nice help for analysis of the relaxation dispersion data using his Chemix software from Guillaume Bouvigny. These sources for funding, and if you're interested in this kind of work, I have an open postdoc position, so drop me an email or have a look at my website. And I thank you for your attention.
Thank you, Malene. It was great. There are already some questions coming in. There's one from Supriya. Ask if you measured the sign of your delta omegas from your relaxation dispersion experiments, since this could confirm the swap of the major and the minor state.
Yes, we did this. So yeah, it was in agreement. So we used both comparison of HSQCs and HMQCs, and we also used off-resonance R1 row experiments to do this. So it was in agreement with the chemical shift differences that we could eventually directly observe in the mutants. And we didn't do this. I presume that this was mostly related to the histidine 493 mutation, so to confirm the swap of minor and minor state. So we didn't do that in that mutant. It was in the wild type before we actually had the structure of the minor state to try and get a picture of what would potentially be the minor state. So there we extracted the signs.
And then also, if you measured the CPMG experiment at a lower temperature where the ring flip would potentially slow down, and you maybe could have measured them without the T1 row, or
yes,
CPMG?
Yeah. So the problem is when you lower the temperature. So we did all of our experiments at 15 degrees to have really nice exchange contributions. They also have nice exchange contributions at 25, but it's a bit fast. So we compromised at 15 degrees. When you lower it to 5 degrees, we essentially have very few peaks left, actually. So the exchange contributions become extremely big, and we lose a lot of peaks. So at 5 degrees, we have to record for a very long time.
Okay. And then there is a question from Jeff Hopp. Very nice, Malene. Back in 1978, in the first 96 picosecond MD simulation of BPTI, ring flips were rare, but it was already clear that flips involved the correlated fluctuations that created voids to permit the flip. So have you explored whether more as modern MD simulation concord with experimental rates?
Yeah, so we did do an MD simulation. So it's 1 microsecond, and we see on average about, I think, 5 or 6 flips during the 1 microsecond. So that would also be in agreement with what we measure experimentally. We also actually try to look at the change in the pocket volume along the MD simulation, but it turns out it becomes very noisy actually. So it is a bit difficult to actually pinpoint if any of these breathing motions are the same as the ones we observe in the crystal structure. So I don't know if it's because the force fields are not really that accurate or what it is. So it's difficult to actually see if there's a direct agreement between the actual fluctuations we see by NMR and those in the MD.
Okay, so as we have a question from Art, you have your hand up. You're mute. Art, you're mute.
Sorry, I wanted to jump in with a follow-up to that question. It looked in the pictures, which of course were ribbon diagrams, that your intermediate breaks hydrogen bonds in the beta strand.
Yeah.
And that strikes me as surprising that that's happening 50,000 times per second. So 2 questions. 1, in the MD simulation, do you see those hydrogen bonds break? And 2, that ought to be able to detect by amide exchange measurements if they're breaking that fast.
Yeah, so I don't have it here, but when you are looking at the secondary chemical shifts of the beta strand, it doesn't have chemical shifts that are representative of a beta strand, actually. So I presume that is really because it's a fluctuating beta strand. So once in a while it has established the hydrogen bonds, and once in a while it hasn't. So I think it's maybe more like a random coil, even if in the crystal structure it appears like a beta strand. And the second question, whether in the MD simulations, whether we see this breaking, I had the root mean square fluctuation somewhere. I don't have it. I think it was larger for this beta sheet, but I don't really remember if I actually looked in detail about the hydrogen bonding.
Yeah, is that okay? A question from Sebastian Hiller. Thanks, very interesting work. Did you test how AlphaFold 2 performs in this system?
This is a very interesting question. Yeah, I did this.
So how did it?
Well, I mean, the overall structure, it gets correct, but it neither predicts the major state nor the minor state. So meaning so it has the major state with the correct orientation, let's say, of the beta sheet with the beta bulges there, but the aromatic ring is in a staggered conformation. So
okay, so it cannot make the eclipse.
No, it cannot make the eclipse. And I guess, I don't know, in the AlphaFold, although I'm not an expert in AlphaFold, but I presume that it very rarely would have sidechain conformations that are unfavorable. So I presume this is why it chooses the staggered conformation, but then of course the structure is not right. But the beta bulge is there. So it somehow managed, it flips out the Q520 to make space for the staggered conformation, a bit like we see in the breathing motions.
Okay. So I saw, Christian, you had your hand up. Is it still a question?
But just go through the questions.
Okay.
And I think we can continue discussing.
So one from Phil Slenko. So does the temperature change the relative population of the major and the minor states? If so, what is the situation at 37 degrees? Celsius?
Yeah, so I think we quantified it at 25 degrees as far as I remember. The population is not extremely different. I didn't, at 37 degrees, the process becomes too fast to be reliably quantified by CPMG relaxation dispersion. Already at 15, you see that we are at 2,600 times per second. So when we increase the temperature, it becomes more difficult to fit the data. So I don't have a measure of it at 37 degrees. I can just see when we are at 40 degrees, I essentially have no exchange contributions left, or very little. They go down, of course, with temperature. So between 15 and 25, it didn't change like loads.
Okay, so what's the reason that all your peaks then disappeared at 5 degrees? Is it that the rate becomes so slow you're really in the coalescence? So
yeah, so I presume it's because the rate goes down, yeah, between 500 and 1,000, maybe something like this, and the exchange contributions become much bigger.
okay. So is it mentioned non-exchangeable protons?
Measure on non-exchangeable proton. What is it?
Maybe 37. Maybe he can drop in later.
Okay.
So then there's a question from Philip Neudecker. He says, hi Malene, do you think ring flips are predicted on the existence of a secondary structure defect, or could this happen also in a regular beta sheet?
So I don't know the connection here with the ring flip. You mean the exchange between the major and the minor state, which is probably because here, could this also happen in a regular beta sheet? I mean, the ring flip, I mean, I'm not sure exactly what he means. Is he around? Or maybe you could.
Maybe he can join later. There's a related question. He also asked, also since the eclipse conformations are so rare, would you expect the opposite case more often, where the major state is the staggered and the minor state is the eclipsed?
Yeah, so I think we are a bit lucky in this case because it was quite easy for us to stabilize the minor state because we were in a rare conformation to begin with. So every time we basically touched any of the surrounding amino acids and disrupted a bit the CH-pi interaction network, we had the transition to the staggered conformation. I'm not sure that you would see a minor state that is really the eclipsed, unless you have a lot of surrounding amino acids that could provide a stabilizing mechanism. Otherwise, I think it's would really be very rare and not observed very often. So I think it really depends on the nature of the surrounding amino acids. Of course, in the beginning, I actually thought that the crystal structure was wrong and had somehow captured the minor state. So this, of course, I also investigated, and it wasn't the case. The major state is indeed the eclipse conformation.
Maybe I can ask a quick question. So we talk about this eclipse state. I mean, we were both taught 25 years ago that this eclipse state is really on the top of the energy landscape. So is there a specific reason why it lands right on eclipsed and not, let's say, half between eclipsed and staggered, where the energy presumably should be slightly more favored?
Yeah, the only thing I can say, I don't know. So of course, this is not the only protein. So no. I think this must be the surrounding amino acids that establish these interaction here, but we could also show, at least now we have two structures within group 1, and you see exactly the same thing here. So this SS3 domain has the same kind of interactions, and it also has this eclipse conformation. So really, I think it depends on the surrounding amino acids, as also is evident in this principal component analysis.
So just to follow up on that, is there any functional difference between the proteins in group 1 and group 2?
Okay, so something I didn't mention is that at least the GIP1 SS3 domain is actually a dimer. So it doesn't have the canonical function, which is to bind proline-rich motifs. So actually in the dimer interface, it covers the proline-rich recognition motif. So it is believed that actually the function of this SS3 domain is oligomerization in this signaling pathway. On the other hand, the POSH here is a monomer, and it's known that this function is to bind proline-rich motifs. So I'm not sure there is a significant difference at least here you have two different functions within group 1. But of course, I don't know. I mean, we cannot exclude that. Of course, all of these eclipsed, that all of the group 1 SS3 domains are eclipsed. We can just say, at least so far, our hypothesis is correct. And maybe it will turn out later that it wasn't correct, but at least for the moment it is.
Okay. There's a question from Rasmus Linzer. It says, "Dear Malene, thanks for a great talk. Because my question is if you can derive anything regarding these structural changes and their effect on the binding of the protein-rich interaction partners." I think you just answered that a little bit. Yeah. As maybe even something mechanistically representative, like a conformational pre-selection for the SS3 domain in general.
Yeah, so as I said, this SS3 domain so far it's a dimer, and it doesn't bind proline-rich motifs, or maybe they have not been identified and they would have to disrupt the dimer. This is also a possibility, of course. So far, the exchange between the minor and the major state so far, of course, we don't know if it has a functional implication. We will have to test in another series of experiments, of course.
Okay, so as Philip made another comment, he said, well, you need the bulge to open the volume for ring flips, right? Question mark. Is this a general theme?
Yeah, so something that I don't think you necessarily need a bulge for the ring flipping. So this is a feature of this particular protein. So I think you can also have, I mean, of course, this is one example of where we have mapped the structural details of the ring flipping. But of course, these structural details will be different for another protein depending on the environment. So we didn't see this bulge is present in a lot of SS3 domains, and that's probably also why AlphaFold actually predicts it. We also tried, one thing that is of course interesting is we looked at this SS3 domain here where we have an eclipse. We measured relaxation dispersion on this. This doesn't have an excited state that we can detect. So here we don't have a transition to a staggered conformation, at least on a time scale that we can detect with those experiments. And we also took a highly homologous SS3 domain to GIP1, which is called GIP2. And also in this case, even if they are 80% homologous, the transition between the beta bulge and the beta strand also does not occur in that one. So it is really a highly specific sequence that does this. And of course, we're looking into that. What is actually driving this? Which particular sequence feature is it? Because if you have a highly homologous SS3 domain where it doesn't happen, you must be able to pinpoint this.